I just want to go over this concept briefly. It doesn't come up very often, but I do think it's kind of important. And that is the idea that if there's no net external forces on a system, then the velocity of the center of mass can't change. So, for example, let's say we have two blocks connected by a spring. The center of mass is going to be somewhere over here on the left edge of the second mass if the second mass is larger. And when they spring apart, this one will have a greater acceleration. This one will have a lower acceleration. So it's going to look something like this. But if this center of mass was at rest initially, then it has to remain at rest if there were no net external forces on the system. Now, there's forces on each mass, but not outside on the system. So the velocity of the center mass has to remain the same, which in this case is 0. So what if they're moving? Let's say we have a mass that is approaching a stationary mass over here. So this mass is 0. Then as it's moving, the center of mass would be moving because this mass is getting closer. When they're actually in contact with each other, the center of mass would be similar to that other situation where it would be a little bit to the right inside the larger mass. So as the center of mass moves, eventually they collide, but the velocity of the center of mass remains the same. And you can see that in these short little video clips. We can see that the center of mass velocity is 0. After the event, the velocity of the center of mass has to be the same, which is 0. And here we can see that the velocity of the center of mass is traveling to the right. After the collision, it continues at the same exact speed to the right. This is a very cool problem. We're not going to do the math on it, but I just want you to understand the idea. And that is, if you launch a projectile, and when the projectile gets to the top of its path, it explodes, sort of like a shell that explodes into two smaller pieces. And those two smaller pieces, let's say the one smaller piece lands short, and the other piece lands further away, the center of mass will actually land where the path of the projectile would have gone if they hadn't exploded. I'm going to do a few integrations to find the center of mass, but there's really only one if you're dealing with the AP exam or most high school, college level classes, where you have to find the center of mass of a rod, but the other ones that I'm going to do are most likely not going to be covered in your course, so you can either skip those or watch them if you're interested. So we know that r com is equal to 1 over m, the integral of r as a vector dm. So that's going to be our displacement vector, but we're only acting in the x-plane, so we can replace that with x. But let's go ahead and look at this rod. So we have this rod of length L. It seems silly to do this because we know if it's uniform density that the center of mass is going to be right in the center. But you might be asked to prove this as an integration. So that's what we're doing. So first of all, what can we say about this rod? Well, we say if the entire rod has a mass m and the entire length has L, that must be equal to a constant that we're going to call lambda, okay? So lambda just represents the mass per unit length. In other words, if we chopped this off, we would have, let's say, a third of the length, we would have a third of the mass. So the ratio of the mass to the length would be the same. So that means if we take a little tiny chunk, that dm, derivative of the mass, then that divided by the little tiny distance there, dx, that would also be the same. So if that's true, then we can rearrange this and just say lambda times dx is equal to dm. So we're going to end up using that coming up in one more step. So let's do this. Let's replace our r com And we're going to do that with 1 over m, and it is in the x-plane, so I'm going to replace that, or not replace, but just insert an I hat. And then we're going to say this is for x, for our distance in the x direction, dm. And now we can insert this because we want an x dx, and right now we have a dm. So that's going to replace us with rcom is equal to 1 over m I hat, the integral of x lambda dx. But we know that this lambda is a constant. It's the density idea. So we can replace that with rcom is equal to lambda over m I hat integral, and we're integrating from one end of the rod to the other. So that's going to be from 0 to L, and then that's x dx. So all we have to do is our integral, which is pretty easy. That's just x squared over 2. So we have rcom is equal to lambda x squared over 2m, that's big M, and that's from 0 to L. So when we sub in RL, that becomes rcom equals lambda L squared I hat over 2m minus 0. Well, we can take lambda, because we know that lambda is equal to m over L. Then we can say m, the mass of the whole thing, is lambda times L, and sub that in here. Well, what's that going to give us? That's going to give us rcom is equal to lambda L squared I hat over 2 lambda L. So we can see that the lambdas will cancel and one of the L's will cancel. So we're left with rcom is equal to L over 2 I hat, which makes sense. Where is the center of mass of a rod or a bar of length L? Well, from here, it's out L over 2 in the I hat direction. This is the integration for finding the center of mass of a semicircle. So this is half of a circle, or half of a thin hoop, and this is optional for the AP curriculum. It's actually really cool. So if you're interested, just watch it because it's a great derivation. So what we're going to do is we're going to start out with this semicircle, and we're going to say that we have the location from an origin right here at the center of, as if that had been a circle, out to this location here. And what we're going to do is we're going to integrate from here all the way around to the other side of the circle. So we're going to add up all of these little DMs. So it's going to be pop, 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 all the way around, and integrate them for that R for all the little DMs. So that's a little DM. Now, instead of using dx, we're going to use ds, because s is arc length. So we're not really using exactly a dx. At a very small distance, it would be a dx, but we're going to use ds for the derivative of the arc length. Now, another important thing before we get too far into this is the distance to this position. Well, right here it's going to be r, but what is it going to be in terms of theta? Well, if we want to get to any location all the way around here, we can go out r cosine theta I hat, and we can go up r sine theta j hat to get to our location at any position. The other thing we need to look at before we start to integrate is the idea of lambda. Now, this is going to be the mass per unit length. So if we look at the mass of this entire thing, and divide that by the arc length of the entire thing, we get a constant. So this is the same idea as in the last integration. Mass per unit length remains the same. Well, if that's true, then for a little mass and a little arc length, that ratio would be the same as lambda. So if we multiply through and we cross multiply lambda with ds, then we can get dm. So dm is lambda ds. Now the arc length, by definition, is r times theta. So if we want to get a d theta in here, because you're going to see we're going to need this, then we take the derivative of both sides. So what's the derivative of arc length? That's ds. And what's the derivative of r theta? That would be r d theta. Then we can take this r d theta and sub it in for ds, so that we have a new expression for dm, which would be lambda r d theta. And you'll see why we need that. Okay, so let's start our integration. We have our formula that we know, and we're going to say r com is equal to 1 over m, the integral of the position, the vector position. Well, what is that vector position? It's going to be the vector x in the I hat direction plus y in the j hat direction, and that's going to be all next to dm. So now what we can do is we can sub in for x I hat, because we know what that is. That is r cos theta and I hat. And then we have our y, we know, is r sine theta j hat. And all of that with our dm. But you can see we have a problem here, because what is changing? Well, r is a constant, so we can factor that out and bring that out here, which we'll do in another step. But theta is changing. We're integrating from 0 over to pi radians on the other side of the semicircle. So we don't want a dm in here. We want a d theta, and that's why we did all of this work. This is to get dm switched over to a d theta. So we're going to take this and we're going to sub it in right there. So what is that going to give us? Well, that's going to give us an r com is equal to 1 over m integral r cos theta I hat plus sine theta j hat, and that's going to be lambda r d theta. That was our substitution. Now we know that this is a constant, this is a constant, and this is a constant. So we can bring all of those outside our integral and leave that as lambda r squared over m. And then we're going to integrate with cosine theta I hat plus sine theta j hat, and all of that d theta. And we're going to integrate from 0 to pi, and that is from one side of the semicircle to the other side. If it was for a full circle, it would be 2 pi. Okay, so now we can do our integration. But before we do that step, we're going to do a couple things at once here. We are going to do a substitution to clean up this stuff. And I'm going to leave it right now as r squared. We'll sub in on the next step. And then we can break this up. And we can break this up into I hat, the integral of cosine theta d theta, so that we're just doing one at a time, plus j hat, taking that out of the integral. And that would be sine theta d theta. And that's from 0 to pi. And then what we're going to do is a little extra side step here. So we're going to say that the total mass is m, and we're going to say multiplying that by lambda times the total arc length, we would get m equals lambda s. But what is the entire arc length? Well, a full circle would be 2 pi r, so a semicircle would be pi r. So that leaves us with m is equal to lambda pi r. And what's nice about this is we can take that and we can sub that in here. So in our next step, we'll write that down there. So now we need to do r com is equal to, and that's going to be r squared lambda over lambda pi times r. That's our substitution in there. And then we need to take the integral of cosine theta d theta, which is sine theta. So that leaves us with I hat, and we better put some brackets in here, sine theta from 0 to pi, minus j hat, and that's going to be cosine theta from 0 to pi. I should have written that little bracket in there. Running out of room on this. 0 to pi and 0 to pi, like that. Now some stuff starts to cancel out. We lose a squared sign with that r, our lambdas cancel, and we're just left with r over pi. So our next step, we have r com is equal to r over pi, and then we have sine of pi minus sine of 0. So what's that going to be? Well, that whole thing is going to drop out to 0. And on this side, we're going to have minus cosine of pi minus cosine of 0. And that was all times I hat, but it dropped to 0, so it doesn't matter. J hat. So what's that going to be? That's going to be r com is equal to r over pi, and then we're going to have this minus sign, then cosine pi minus 1, minus cosine of 0, 1, all times j hat. So what does that give us when we do all these minus signs here? The minus 1 is going to be minus 2 times minus is going to give us positive 2. So we have r com is equal to 2r over pi, and we're left with that j hat. Now, where was the origin of our problem? Well, we had our hoop, our semicircle hoop like this, and our origin was here. So where are we going? Well, we're going 2 times the radius divided by pi. So that's going to put this somewhere in there, j hat straight up. So that's the location of the center of mass. Let's see. Our goal here is to integrate and find the center of mass of a hoop. You thought it was what?
You said it was a really thin donut.
Okay, it's a really thin donut. It's this, all right? It's that. So to do this, we are going to use the formula RCOM. And what's the first thing that we need to do?
Origin.
We got to choose an origin. Okay. Now, if you think about this, if we chose our origin to be here, and we were going to integrate, we're going to add up all those little masses, all these little masses, we would then have to add them up, and this not only would the position be changing, but the length of this radius arm would be changing. So this would be bad, right? So what's the one place where we can get, at least keep that variable the same, the radius? And that would be at the center. So we're going to make 0, 0 to be our origin. Okay, this actually is a very, I just don't want you to get depressed because this derivation has a sort of depressing ending. But it's an easier one. We'll get to a better one later.
Well, yeah, because it would just be negative. It would just like cancel out.
That'd spoil the depression.
The journey.
Okay, so let's see. We've got this little chunk right here, and what's the mass of that little chunk?
dm.
It's dm. It's little m. Okay, and what is the length of that section? What's the section of a curve?
Arc.
An arc. Okay, and what's the length of an arc? S. Okay, and what's a little tiny bit of an arc? ds. So that right there is ds. All right, good. Now we want to integrate. We want to go out to this point and then find out. We're going to add up all the little masses for these different positions. So we've got to describe that position. Well, how do we get to that? How do we tell this radius where it is to be? Well, we can set this up with theta and then use theta to sort of give us an x and a y coordinate. So what's this side of the triangle?
Cosine.
Okay, it's going to be x equals r cosine theta, and then we've got y, which is r sine theta. Okay. So really, when we write this r com, we're doing this for x I hat plus y j hat dm. And we are giving this a location. And what's that location? Well, it is r cosine theta I hat plus r cosine, whoops, no it's not, sine theta j hat. And all of that dm. What's changing? What's changing in here?
Theta.
Theta is changing. What's r doing?
Constant.
It's a constant. Can you see why this would have been bad if we had picked this as the origin? What else would have been changing? R. And then we would have had a variable, and we would have had to integrate them. But now what can we do with r? We can take it out because it's a constant. Okay? So we have theta is changing. What's our problem here? We've got dm.
Should be theta.
We need this to become a d theta. So we have to do some trickery to get rid of that, okay? So we're going to do this as a little side step here. This is all going to be in the cloud. What's the density of this hoop? What's the density of the hoop? It's the mass of the entire hoop divided by the arc length of the entire hoop. So it's going to be m over s. And what symbol do we use to represent density?
Lambda.
Lambda. Okay. And if we took a little chunk of this, a little tiny chunk, for a little tiny arc length, that density would be the same. So that's also equal to what?
dm.
dm over ds. All right, good. But what do we need in here that we still don't have?
Theta.
We need d theta. Okay. So to do that, we're going to use a definition. What is the length of an arc? You guys should have learned this at some point. What's the length of an arc? It's r theta. You guys remember this? Okay. So S is equal to r theta. We need to get what though? Not theta. We need d theta. Okay, so let's see. D theta. So why don't we go here? What's the length of a little piece? What's the length of ds? What's that?
D by theta.
dr theta
Would it be RD theta?
rd theta. You just got to put the d next to the theta, not the r. So that's going to be ds is equal to r d theta. That's the, that would be d theta in there for that little tiny thing. So now what can we do with that?
Plug it in, yeah.
Yeah, we can plug that in for ds. So now we have lambda equals dm over r d theta. And what's dm then?
And
Yeah, good. Lambda r d theta. And what are we going to do with that?
over S.
We're going to put that in for dm. Okay? So let's see. All of this is a side step. So I'm going to put that inside a cloud. And let's rewrite this step. So this becomes rcom equals 1 over m.
Can you plug the R?
Yes. Pull out the r, and then we've got, let's see, the integral of, then we've got cosine theta I hat plus sine theta j hat, and we're going to multiply that by, now for dm, that's going to be lambda r d theta. Where'd the derivation go? What? Okay, we're moving on. All right, so this was the last step that we had. What are we integrating from? From what to what?
0 to 2 pi.
0 to 2 pi. So we're integrating from here, and we're going to integrate all the way around the circle. So one full circle is 2 pi. So let's put in 0 to 2 pi. And what's constant stuff?
Lambda.
Lambda, density is constant, that's not changing. What about R?
Yep.
R is constant, so let's bring that stuff out. So that's going to become rcom integral, let's see, lambda what?
R squared.
Good, r squared over
M.
m. And then I can break this up, right? If I have a plus sign there, I can then distribute and say, I'm going to take the integral of cosine theta separately from sine theta. So that's going to become the integral cosine theta I hat, 0 to 2 pi, plus the integral 0 to 2 pi sine theta j hat, and d theta, d theta. Okay, tell us what we're integrating on. Okay. All right, now we can do our integral. What is the integral of cosine theta?
Sine.
Sine theta. What if you didn't know that? How could you even know that? You could ask Mr. Agro, yes. You could ask Mr. Hodges. You could also just look on your reference table, okay? What? On the calculus page, it tells you integral of sine x dx. Wait, what was cosine? Integral of cosine x dx is sine x. So you don't actually have to think for that step. So let's do that. That's going to be rcom equals lambda r squared over m. You know what? I'm not going to put that m in just yet. Okay. And then what's the integral of cosine theta is sine theta? So that's going to be sine theta I hat from 0 to 2 pi. And what's the integral of sine theta?
Negative.
Look it up. It's negative cosine theta. So that becomes minus cosine theta from j hat from 0 to 2 pi. Okay, the reason I'm not going to put the mass in right there is because we can actually get the mass of this thing, right? Remember that that lambda is equal to m over s, right? I think this was maybe the mistake that I made yesterday. Okay, so the total mass is equal to lambda s. That's total mass. Right? And how much do we have? What's the arc of the total thing?
2 pi.
It's Well, it's 2 pi. What is that distance?
It's 360.
Okay, and so what do you call this in a circle? Circumference. And what's the length of the circumference? It's not 2 pi. 2 pi r, yeah. Okay. So that's going to be m equals lambda 2 pi r. So I can take that. Let me see if I can sneak through there. Okay. And put that in right there. Okay. So then that's going to be lambda 2 pi r. Okay. And that's kind of nice. Squared side's gone, r's gone, lambda's gone, lambda's gone. So we're getting close here. And now we can actually do this. I'm going to come over here. So we've got r cone. I've got my vector sign. That's r over 2 pi. And well, we have to do this. So that's going to be sine of 2 pi minus sine of 0 minus cosine, that's all I have, minus cosine 2 pi minus cosine 0. I think we're still doing okay. That's all j hat. That's still all I hat. Okay, what is sine of 2 pi?
0.
It is 0. What's sine of 0?
0.
0. So that's 0 minus 0. So that's gone. And then here we've got cosine of 2 pi.
1.
That's 1. And what's cosine of 0?
1.
1. So we have r over 2 pi. I told you it was depressing. Minus 1 minus 1. Right?
Yes.
And that ends up becoming what?
Negative r.
Oh, is that negative 0? What's 1 minus 1? 0. So that becomes
0.
0.
Wow.
Okay. But does it make sense?
Yeah.
Does it make sense? Look, where is the center of mass of a hoop? It's in the center. Where is 0, 0? It's in the center.